Okay, now we're talking about electric potential, and then we're going to turn that in. Okay, now we're talking about electric potential energy. So the first thing is, let's say we have a negative charge here. Okay, if I have a negative charge, negative, 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 like that, it's going to have an electric field that is coming inward, because again, it's going to go towards the direction a positive charge would move. So the electric field lines are going to be there. Let's put a positive test charge right here. And I'm going to label that point A. Now naturally it's going to be attracted to the left. But what I want to do is move it out to a place to the right. I want to move it to B. So in order to move it to B, I'm going to have to add some force to it. And if I push and 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 I move it all the way to that point, I've had a force acting over a distance, so therefore I've done work. And we know that work is equal to F times X. But the key thing to understand about work is really just energy. I did energy to move it out to that larger area. So when I move it out to point B, I now have more energy. I did work. I used energy. I've got less energy in my body now. We know energy has to be conserved. Well, what happens now is B has more electric energy. It has more electric energy because it's farther away from our big negative thing. Remember, if I let it go, it's going to try and go back to the negative charge at the beginning. Now, this corresponds very well to gravity. Now, what's going to happen with gravity? Let's say this is the Earth, and I have a mass sitting on the Earth, and I want to lift it to a higher thing. It's in a gravitational field. Remember, the gravitational field is pointing down. We're familiar with that, little g. Okay, now, in order to make it move, I'm going to have to apply an upward force. I'm going to have to do work. Force times X is equal to work. But in this case, what I'm doing is I'm gaining potential energy. Well, force is M times G, and the X is what we commonly call height. So when I push it away from the gravitational 0 point, and again, we can pick 0 wherever we want, it gains energy. Same thing with electrons and electric charges. And as we've said before, when you move a charge from point A to point B, at point B it's going to have a higher potential. And again, it's going to have a higher potential energy, but potential energy depends upon the charge. The higher potential is based just on the location of the thing. So now if I have a Q, a charge there, and it's negative because the electric field lines are pointing in towards it, and I have a positive charge out there, in order to lift it, I have to do some work. So to lift it to there. Now I've lifted it to a point where it has more potential energy. It's electric potential energy. It's farther away from the charge. So therefore, remember, it's being attracted to that negative charge. So when I let it go naturally, it's going to move towards that Q. And then I can convert that falling energy, that falling charge, Q can do work. Okay, now let's talk about the difference between force, energy, potential, and field, and see how they're related in our two systems. Here I have a gravitational system, right here. I have a mass M sitting on the surface of a planet. A G is going in all directions. Gravity sucks. Over here I have an electric charge. I have a positive and a negative, so therefore this side's positive, that side's negative. The E field lines give you an idea of how it is. Key thing is we're talking about uniform fields right now. We're not talking about a changing field. We're keep our distances small enough where it can act like a positive thing. So let's go ahead and take a look at it. Well, we know force, and let's start with force, because we know force in the gravitational thing is M times G. Force in the electric system is equal to Q times E. No difference really in those two, except one we're dealing with masses, one we're dealing with charges. Now, to go to work or to go to energy, I'm going to write out the word energy, I'm going to do it with respect to the distance it travels. Essentially, you're integrating over distance, but I don't want to mention calculus words. So what I'm going to do when I make that jump is I'm going to say energy is equal to m times g times h. Over here, it's q times e times d. Now, there's a convention in here that they use in electricity, which I almost wish they didn't use. When we're talking about h over here, we're talking about the distance against the field. Again, because we're lifting the objects up, we're talking about the distance against the field. So our h is a positive value, even though g is acting down. Over here, we switch that. We say that d, let me change that. We say d is the distance moved with the field. D with field. Now, what that means essentially is that if I have a charge here and I move it with the field, well, that's the way a positive charge is normally going to want to go. So if I have a negative charge, I have to put a negative sign in there. So therefore, we'll commonly see that with a negative sign tacked in there. It's just a convention on how they're defining distance. Okay, now, let's from here go from energy to potential. And to go from energy to potential, we're going to divide by m or q. Remember, those are the analogous things in the two charges. Mass and charge essentially are the same thing. They are the things that feel the forces. In a gravitational field, the masses feel the gravity. In an electric force, it's the charge that feels it. So I'm essentially going to divide by m. So if I divide by m, I get GH. Now, GH is not something you've really ever seen, but it's really the potential at one point. It does not depend upon the mass. Usually, we don't tend to worry about that too much from a gravitational point of view. But if we have a certain height and a certain g, all of us would have the same potential, but each one of us could do different amounts of energy based on our mass. Well, the same thing happens with energy over here. Now what I'm going to say is I'm going to divide by q, so I'm going to get negative ED for potential. And that's got a name, and it's one of the most important things we see. Dun, 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 dun. Voltage. Voltage is nothing more than the potential. Notice how it does not depend on how much charge is there. That's why voltage is joules per coulomb. You need to know the total amount of energy, you need to know the amount of charge that's there. But there's a certain amount of potential based where you are, and the farther you are away from an opposite charge, the more potential you're going to have. The last thing I want to do is I want to go from potential to the concept of field. Let's change that back to red. So let's get rid of that. Let's change it back to field. And I'm going to use field. And what I'm going to do now is essentially differentiate with respect to distance. Again, I'm talking about things that are moving up and down in the field. I'm not talking about things that are moving sideways. You don't change your potential by moving sideways. You change it by moving up. So if I differentiate with respect to distance, and I essentially get rid of the h because it's a linear thing, and I get g as the field, which is what we've always known. If I come over here and do the same thing, what I'm going to have over here is the field is equal to E. It's beautiful how they're related. And I think you'll find potential a lot easier if you think about it in terms of that. Potential has got another name, it's called voltage, but it's really nothing more than the electric potential at a particular place. Notice how it does not depend on how much is there, how much total energy the object has at that place. You've got to add Q in, and you have to go to this equation up here. to get the total amount of energy, because that's going to be Q times the voltage. So that's useful and something we'll see in the next video.